Okay, so the plan today, pretty simple, just finish up chapter one. The chapter one PowerPoint, we have a few slides left to go, and then start into the chapter two PowerPoint. So chapter one is just kind of generally about an introduction to some of the ideas that we're talking about in the course. Chapters two and three really start to dig into descriptive statistics. Chapter two more in the graphical or visual side of things, and chapter three more in the numerical side of things. So we'll start the chapter two PowerPoint. There will be a PowerPoint presentation for chapter two because it's more kind of visual and graphical oriented. We'll also do some examples on Excel in chapter two. So again, as I had mentioned previously in the course, if you're not at all familiar with Excel and you want something that's a little more formal and a little more guided, there's that Coursera course in the Useful Websites tab. You can go in there, you can audit it for free. You don't have to pay them any money or anything. And I think that's a good resource if you want something a little more formal, a little more guided to introduce you to Excel. And if you're, a little more willing to kind of go it on your own, you can use the combination of what we do in class, what's in the textbook, and just some, Googling for things that if you're not sure how to do something, you can just Google it and get some extra information there. Or, of course, as always, stop in office hours, send me an email, anything like that. So that is the plan for today. Starting in chapter three will not have a PowerPoint because it's more kind of numbers based. So we'll be doing, it'll feel a little bit more like a math course. So we'll be doing a little more kind of board work, so to speak. Chapter four, we'll go back to PowerPoint. And then chapters 5 and 6 will be kind of back to board work. So we'll be flipping back and forth between PowerPoint depending on the chapter and what works best. But for chapter two, we do have a PowerPoint, so that's available on that PowerPoint as well as the Excel files we'll work through are available on Blackboard. And just so I don't forget, I will pop those into the chat. Let me do that really quick here. Okay. So there's the PowerPoint in the chat and one of the Excel files that we might get to or might not get to today, also in the chat. All right, so and they're also available on Blackboard. So if you don't grab them from the chat, no big deal. And also lots of things to discuss today on the front end of things. Chapter two homework is available on My Stat Lab. Note that for the chapter one homework, you had unlimited attempts per problem just to kind of get acclimated to the system. But starting in chapter two and for the rest of the course, you're limited to 5 attempts per problem. So, that should be enough that if you're understanding the material pretty well, that you should be able to work out the answer within 5 attempts. But, I do recommend against using the homework to learn the material. The homework really should be an assessment of how well you know the material. Ideally, you do the homework after you feel like you have a pretty good understanding of the material, and the homework might point out, shortcoming here or there that you might want to correct. So that's really the goal of the homework. Okay, and our quote of the day today. I saw a recent quote of the day in an email that said something like, what was it? The road to success is always under construction. And I thought to myself, well, I mean, I kind of see where they're going with that, but I don't know. I feel like that could be taken the wrong way pretty easily, especially with Pittsburgh's, famous construction complaints. So we'll go with a different quote of the day. This one is a paraphrase of Ralph Waldo Emerson. And the quote or the paraphrase is, "What you do speaks so loudly that I cannot hear what you say." Right? It's kind of like actions speak louder than words, but really bringing that to the nth degree, saying actions are so much more impactful that when the action contradicts the words are almost meaningless, right? And so just a couple questions to think about. I think these are good things to check in every once in a while, maybe every couple months or, at least once a year. I guess we're kind of in New Year's resolution time, more or less still. So this might be a good thing to check in with, but, ask yourself if you were to write down, say, a paragraph or something or a short list on a piece of paper and you say, what things in your life do you value most? What is most important to you in your life. And then if you were to take an account of where do you spend your time, your energy, your money, your talents, you know, your efforts, your emotional resources, cognitive resources, all of these things, where do you spend the majority of those things, right? It's very easy to say, get sucked into like a social media rabbit hole and spend a whole bunch of time on, you know, TikTok, or I don't know, is TikTok banned? I don't know if it's like actually banned or not, or it's kind of confusing. You know, TikTok or YouTube or if you're old like me, Facebook. Um, right. It's easy to, you know, to kind of get stuck into those time sinks, especially today. Um, and, you know, if you see a discrepancy, if you see that you're spending a lot of time, talent, and treasure on one thing or one group of things, and they are very misaligned from the things that you value the most, if the things you value the most are getting dropped in favor of these things, maybe, you know, that's something to at least be aware of and maybe try to make strides to close that gap. So I think it's useful to check in every once in a while on that and just evaluate that. All right. So jumping back over to the chapter 1 PowerPoint, let me rework my windows here. Oops. Let me just redo the share. Okay. All right, there we go. All right, so this is where we left off last time. Well, let me shrink this down a little more. There we go. This is where we left off last time. Uh, we got right up to misuses of statistics, but did not start it. And I kind of have these misuses of statistics broken into 3 slides here. As kind of an aside, there's a couple of books that are kind of fun little reads. I want to say maybe 100, 120 pages each. They're um, just kind of, you know, they're not very technical books. They're one of them is written almost like a comic book. One of them is called How to Lie with Statistics, and it's like an instruction manual for how to lie with statistics. It's kind of a tongue-in-cheek way of saying, hey, these are some statistical misuses that you might want to look out for when you're digesting information. And the other one is, I actually have it on my bookshelf back there, Statistics You Can't Trust. So Statistics You Can't Trust. Both of those are fun little reads, you know, little short, you know, read them in an afternoon kind of thing, or like, you know, put on your bed table and, um, you know, read for 15 minutes before you go to sleep or something, and you'll have it done in a week, and, you know, those kind of things. But those are fun little resources if you're interested uh, in anything else on this. And I think it's also important to discuss when we're talking about misuses of statistics, the person presenting the misused statistic could be malevolent. They could be intentionally trying to mislead you, but they might not be, right? So just because you trust somebody, just because you say, hey, this person's incentives are aligned with mine, or they have no reason to lie, or I trust them because, you know, that they've said a bunch of stuff in the past that's truthful, they could very well just be making a mistake too. So you don't want to assume that somebody is not misusing statistics just because they're trustworthy. And I suppose, you know, probably on the other side of things, you maybe ought not assume that somebody is misusing statistics just because you don't like what they say or because you don't consider them trustworthy. Um, Although that would certainly make me a little more skeptical and a little more likely to dig into the claim for better or worse. Okay, so I've kind of roughly divided these into 3 different slides. The first one has to do with samples, you know, things with the data collection methods in a sense. One is choosing sample size, right? If I want to say something about the population of people in Pittsburgh, a population that's something like 500,000 or something, you know, maybe 1 million people, depending on how you define the Pittsburgh area and all that. If I take a sample of size 3, that's probably not going to be a very good representation of all the people in Pittsburgh, right? If you think of just if we're talking about heights of people, there are older people and middle-aged people and younger people. There are males and females, and I mean, just there we have basically six groups, right? Old, young, and middle-aged for both males and females. We certainly can't cover all six groups with just three people. But we can think of slicing and dicing things a number of other ways as well. And we kind of want a representative sample. So we want our sample size to be large enough that we can consider that, okay, if I take my sample randomly, my sample looks kind of like the population of Pittsburgh, but just shrunken down to miniature. That's kind of the idea of a sample. On the other hand, on this kind of sample size note, if I see one of these research papers with humongous sample sizes, tens of thousands of people, they just data mine electronic medical records, things like that. That kind of brings up some other issues. And they're a little bit technical, so I think they're better to discuss maybe a little bit later, say after we've gone through some of the hypothesis testing material near the end of the course. So that's when we'll discuss those issues a little bit. But kind of roughly speaking, when you have a huge sample size, tens of thousands of people, um, little teeny tiny differences that aren't really important can be magnified and can look very important in some sense. So we want to be careful of samples on either end, for the small end samples, or even at the extreme, in that case, a case report, something's published in the literature and it says, hey, this happened one time. Well, you should read that as this is a possibility, this is a proof of concept, this is something that could happen and is maybe interesting. But if if you're a doctor and you walk into the room with your patient and you see they have these symptoms, you're probably not going to jump to that, N of one case report example and put that, diagnosis high in your differential. So, so sample size, especially be wary of small samples. They're probably not representative. Another example is faulty survey questions. A question can be phrased in such a way that it leads a person to one answer or the other. One kind of, I guess like popular example of this is that the pollsters, whenever they're doing political polls, they randomize the order of the candidates. So, if somebody is saying, do you vote for, or do you plan to vote for candidate A or candidate B? Maybe because candidate A is listed first, for people who are just kind of on the fence, that might, just seeing them listed first might bias them one way or the other. So half of the surveys they'll say, or do you plan to vote for candidate A, candidate B? And then the other half they'll flip them so that candidate B is first and candidate A is second. So things like that, right? On kind of the extreme end of that, there was a kind of a science literacy survey, I guess survey or quiz or something like that, put out by actually a pretty good polling company, Pew Research, if I remember. I think it was Pew. And it was 10 questions about science topics. So things like, hottest layer of the sun, things like that. And basically, at least two of their questions on there simply were incorrect from a science standpoint. If you were reading the answers using the science words they were using in the technical sense in which scientists describe them, things like temperature isn't the same thing as heat. The answers they were giving were simply wrong, or at the very least, not clearly correct. So, so yeah, you have to be a little careful with that, right? If you're putting out a survey like that, and especially if you're saying, we want to decide how many people answered each of these questions correctly versus incorrectly to get some understanding of science literacy, well, you got to make sure that your answers are actually right, or that your survey questions are well posed. And then simply input errors. You go out, you measure somebody's height, and it measures as 5'10", but you read the measuring tape wrong, or you communicate that to somebody else and they just write it down incorrectly, something like that, right? So input errors, Unfortunately not, I don't think a whole lot you can really do with that except just be careful. But that is, something that we want to be careful of. Okay, we have this slide on bias, and we're going to spend a little bit of time here. So this is kind of an interesting little slide. We talked a little bit about bias earlier. And remember, we said that bias what is what we call it when some measurement of a sample deviates systematically from that measurement in the population. So if we were, say, measuring the average height of people in our sample, and the reason that we're working with a sample instead of a population is because we kind of have to, but we're hoping that when we say compute the average height of people in our sample, or maybe the maximum height, or maybe something like the variation in heights in our sample, we're hoping that that number that we compute for our sample is going to be pretty close to the actual number for the population. But when there's bias involved, then we're going to be systematically different. So for instance, one kind of silly example that gets to the point is if I pulled my sample from a grade school and measured a bunch of people from a grade school's height, I mean, I might get a couple teachers or something like that who are adults, but most of them are going to be kids. And my average height from my quote sample is going to be much lower than the average height for the population of all people in Pittsburgh because I've got a whole bunch more kids in my sample, a much higher proportion of kids in my sample than the proportion of kids across all of Pittsburgh. Um, or, if I went to a basketball practice for a college team or something like that, I'm probably going to get biased height data the other direction, right? These folks are all going to be quite tall. And my sample average is going to be systematically higher than the population average. So that's one example. Yeah, so selection bias. The question is, how do I select the folks that I'm using for my sample? And, picking kindergartners or a basketball team as my sample for, say, height data, probably not a very unbiased choice. That would be an error in selection bias. The next one, confirmation bias. This is perhaps the most insidious one. It's in a sense what the scientific method tries to battle against, at least in some sense. And it's the bias that probably everybody has and probably most people think they don't have. It's the bias where when we believe something to be true and we get more information from the outside world, the information that is in line, that's concordant with our belief, we accept it and we say, oh, look, see, I knew it was true. But when we see information that's discordant with our belief that would tend to argue against our belief or even completely overturn it, we just reject that information. We just dismiss it. Oh, that's from an unreputable source, or that's just one data point, or that's just a fluke or something like that, right? So once we are entrenched in an idea, once we have a certain belief, we tend to reject evidence that would conflict with that belief, and we tend to readily accept evidence that is concordant with that belief. And that's confirmation bias. So we enter this kind of positive feedback loop where we believe something, and then, 6 months later, if you evaluate the data that we've taken in a sense, we've taken in all of the data that supports our conclusion, and we've kicked out all the data that doesn't support it, and then we believe it even stronger. And then 6 months later, it's, even stronger still, and so on. So the idea of the scientific method, kind of roughly speaking, is take the thing you believe and try really, really hard to prove it wrong. That's, philosophically maybe the idea behind the scientific method. You're trying to prove your idea wrong instead of looking for evidence to prove yourself right. And I kind of listed in here, it's a little bit of a fuzzy notion of bias, right? Like, if I'm measuring people's heights in Pittsburgh, I mean, that's pretty objective data. It's going to be pretty hard for me to apply confirmation bias there. However, in some, cases, like okay, I think that whatever red color cars run red lights more often than blue color cars because the people that buy red color cars, they're all like, speed demons or something. And well, if a car goes through if I'm sitting in an intersection just observing what's happening, and if a car goes through kind of on the orange, so to speak, right? Do I call that running a red or not? Maybe because I, you know, have it out for the red cars, maybe when the red car runs the orange, so to speak, I tick the red car as, yep, red car ran a light. And when the blue car does it, oh, he was close enough. That's not running the light, right? So we can see how confirmation bias could impact the data, the data sets that we end up with. Survivor bias is a really interesting one. And let me switch my screen share once again. Actually, let me just pause it. I think I might have actually in my quest to close as many tabs as I can. No, actually I didn't. Okay. I didn't close the Blackboard that I wanted to bring up. So in Blackboard in this um, PowerPoint presentations, we have this picture here, this walled plane picture. And here's a little story behind this picture. Can I get it all in one picture? Yeah. Okay. So here's the story behind this picture. So Abraham Wald was a statistician. Back in World War II, he was working with the Royal Air Force, the UK's Air Force. And basically what they said is, okay, we're in combat with what were they, the Axis, the Allies versus the Axis. And we want to beef up our planes, right? Our planes are getting shot down. We want to put some armor on them. The thing about a plane is you can't turn your plane into a tank because then it can't fly. So we can't just like put armor, a whole bunch of armor all over the plane and won't get shot down, but it'll never make it off the ground. Or at the very least, the more armor that we put on, the less maneuverable it's going to be. That's going to be a detriment, right? To less maneuverability, less ability uh, to either avoid getting shot in a dogfight or to attack your opponent. So so basically these folks asked, they said, hey, Wald, where should we put the armor? So what Wald did is he sat on the side of an airfield and he watched the planes fly out. So plane flies out, gets in a dogfight, plane comes back and lands. And when the plane lands, when it comes back, he writes down or notes on a little, piece of paper where the plane had new bullet holes. Where was the plane shot? And on this picture is a kind of schematic representation of his findings. So these are where planes that came back and landed had been shot. He noted in his little notebook and says, okay, on this, he makes a recommendation. This is where we should put the armor. So any thoughts on where we should put the armor based on this picture? As an aside, I don't have chat up because I'm in full screen. So you can just unmute yourself if you have a
Not
suggestion.
where the bullet holes are,
So it's interesting that you say not where the bullet holes are. Why is that?
because those planes survived. They made it
Exactly.
through.
Exactly. Yeah, that's exactly the point here is we're looking at survivor bias. These are the planes that were able to take a hit in, say, the edge of the wing here, or maybe in the middle of the fuselage. They were able to take that hit, come back, land, maybe get repaired, or, they didn't get shot down. Presumably, I mean, especially back in 1940 or something, um, they were just kind of spraying bullets at one another. So you would expect if you were to look at all planes that went into dogfights, kind of a uniform distribution over the whole plane of where it got hit. But we noticed that like the planes that got hit in the cockpit, we never really see any of those come back. The ones that get hit in the engines, never see those come back. The ones that get hit in the tail gunner area, the tail gunner's probably shot. They, have lost half their defense now. Those ones don't come back. The ones that get hit in the edge here of the wing, or I should say in the middle of the wing, where the fuel is often stored, those ones don't come back. So yeah, exactly. So we're looking at the survivors. The survivors are the ones that can take a hit here or here or somewhere else. So we'll presume then that the ones that were shot down that didn't survive, those are the ones where we don't see the hits. So we want to armor the areas where we don't see the red dots. And so it's a little counterintuitive, but when we think about it, it kind of makes sense though. A couple other interesting examples of survivor bias. One of them is, so people look at hedge funds. Most folks know what a mutual fund is. It's kind of like where a bunch of people pull their money together and then invest in, certain groups of stocks. So you might, if you have a retirement portfolio or something, or your parents have a retirement portfolio, they might invest with, a company like say PIMCO or like Vanguard or something like that, or Fidelity. So that company will pull your money together with a bunch of other people, and there will be a manager, they'll buy stocks and so on. And you look at these mutual funds, which are kind of the normal kind of funds that people invest in, and you compare them to hedge funds, which are funds that do things that are a lot more risky. They're kind of like the cowboy finance, versions of mutual funds. And you look at the performance of these hedge funds over time, you look at the ones that say exist today, and you say, wow, they've done so much better than mutual funds over the last 20 or 30 years. And you say, well, I want to invest in a hedge fund, right? Because they're doing so much better. And there's all kinds of, legal technicalities to that. But besides that, remember, we're looking at the survivors. Mutual funds just do kind of normal stuff. They don't really go bankrupt. But hedge funds, they take big risks. And, some of them make it big. Some of them do really great, but some of them actually go bankrupt. So the ones that we're looking at today, the cross section we're looking at today over the last 30 years, are really the survivors. So of course the survivors have done well. But if we're making the decision, we don't get to make the decision today where I can pick somebody who's a survivor 30 years from now. I have to pick from the group who will be survivors and the group who will not be survivors, and I might pick the wrong one and lose all my money. So they're a much more high risk investment on the front end. Of course, on the back end, if you could pick somebody who you knew was going to be a survivor and wasn't going to go bankrupt, then that would be the play, but not all the time. Another example from the medical field, I think we have some folks going into medicine in here. So the sickle cell trait, which is kind of one bad sickle cell gene, but not two bad sickle cell genes. So folks with sickle cell trait don't have sickle cell disease, but they're in kind of a loose sense a carrier of the mutation. They actually have a survival advantage against malaria. So basically the I guess you call it a parasite. I'm losing the specific word, but the malaria bug, let's say, it's unable to or less able to replicate inside of red blood cells that have sickle cell trait. So there's a survival advantage to if you get malaria, if you have sickle cell trait, you're more likely to survive than if you don't have sickle cell trait. But on the other hand, if you have sickle cell disease, two bad copies of the gene, that's very detrimental to health. So we see that the sickle cell trait is much more prevalent in the African American population in the US. And that's because of their historical connection to Africa, where malaria is endemic or at least a much bigger problem. So we see that relationship. I think there's maybe some kind of a similar relationship with the thalassemias and the Mediterranean. So the alpha and beta thalassemias have kind of a similar survival relationship with the Mediterranean area. So a few different examples of survivor bias. Estimator bias, I'm going to give an example here that's kind of a silly example, and then I'll give a little bit less of a silly example. But estimator bias has to do with how we mathematically compute the sample estimate, the sample statistic, on the basis of our sample. So suppose we're interested in the average height of people in Pittsburgh. Again, ideally, we would be using the population. We're stuck using a sample. So we take our sample, let's say that we do it in a good way. So it's a nice representative sample, reasonable size, all of that good stuff. And I think most of us kind of know how to compute an average, but just a reminder, the average is the sum of the data points. So we'll call it x1 plus x2 and so on plus xn divided by the number. So if I had 10 people's heights I was averaging together, I would add up their heights, divide by 10, that's the average height. But let's say that for some reason I did this and then I subtract 5 off the end for some silly reason. Maybe I just made a mistake in my Excel file and had the wrong formula in there, or maybe I thought this was the right way to compute an average. Well, because of the way that I'm computing this average, anytime that I compute a sample average, it's going to be biased to the left. It's going to be a little bit smaller than it really ought to be because I'm subtracting 5 off. So that's what we mean by estimator bias. This thing, this sample average, is what we call an estimator, and it's inherently biased by the way it's calculated. Now you might say, well, this is kind of silly. Who would ever do this? Well, you might make a mistake again in an Excel file or something like that, or in a computer program, you might just type it in wrong. But a more insidious example is with the variance. So for the sample variance, we have some numerator, kind of like the average up above. Oh, is there a question? If there's a question, I'm not hearing it come through. Okay, I don't think so.
I have Guinness on my mind.
I think either somebody unmuted themselves accidentally, or if you're trying to ask a question, I'm not hearing it clearly. Okay. All right, so with sample variance, you have a numerator that's a little bit complicated. We're not going to get into it now. That's a chapter 3 topic. And it would seem quite reasonable to divide by n, just like we did here in an average. But it turns out that if we divide by n, we end up with a biased statistic. We actually have to divide by n minus 1 to make an unbiased statistic. It's really kind of a strange thing. It's not something that we would expect at all. It's not nearly as silly as this like subtract 5 off the average kind of thing. We would expect that you just divide by n, you get something perfectly reasonable and unbiased, but it turns out that that's not the case. So the sample variance is the kind of canonical example of estimator bias. For us to get an unbiased estimator, we need to divide by n minus 1 in the sample variance, even though in the population variance that we compute a very similar way, we just divide by n. Okay, so these last couple, I'm going to go through a little more quickly than the first half. Detection bias, some things are hard to study because they're hard to find, right? If you're interested in crime, what are crime statistics, looking like? Well, if you go up and start asking people like, have you committed this crime? Like everybody's going to say no, even if they have, right? So the ability to detect people who have committed a certain crime is going to be a little bit harder. Or if you're interested in studying, say, an endangered species, well, if you're studying some like, big, bright colored, loud parrot, if there's one around you, you're much more likely to see it than if you're studying some like, little snail or something like that, right? So the ability to detect a thing if it's there plays into this detection bias. There's an interesting example with the Kepler project, which is looking for planets that are kind of like Earth in other solar systems. I suppose they're not solar systems. I think solar systems is just ours, but similar, star systems to ours. And it turns out that they have to correct for this detection bias because they're able to detect planets that are kind of on transit paths that are like parallel to Earth that put like that planet between its star and Earth, but they're not able to detect ones that are at other angles. So they have to look at the ones that the transit paths they do see, and then make inferences about how many total planets are there that they didn't see that might be on a transit path that's not parallel to Earth in some sense. Reporting bias is another one to always keep in the back of your mind, that if somebody makes a discovery, what's their incentive, right? In some areas, like say finance, if you make a discovery, if you figure out a way to make money in the market, it doesn't make a lot of sense for you to publish it, because by keeping it secret, you can use it and make money. If you publish it and let everybody know about the idea, well, then it loses all of its value, right? If everybody knows about it, everybody's going to try to do it, and you can't have everybody get rich at the same time. Obviously, that just doesn't work. So you lose your competitive advantage. On the other hand, in areas like, say, medicine, if you get a big grant and you do some research project and it just completely flops, what you expected to find just did not come out the other side, the chance that you're going to convince some big publication, Nature or Lancet or JAMA, to publish your finding that was just like, okay, we didn't find anything interesting, is pretty small, right? They want to publish the big, new, interesting findings. So there's a reporting bias there that's in the other direction. So status quo bias, just kind of very quickly, we tend to give more favor to things that are the same as we've done in the past than things that are different. I think this probably ties in a little bit with confirmation bias as well. And there's this interesting idea in medicine of lead time bias. So let's say, we look at the average life expectancy of a person who gets a certain type of cancer, say 10 years ago versus now, or maybe let's say 10 years ago versus 20 years ago, so that we actually have some time to study it. And maybe we found that from 20 years ago to 10 years ago at the diagnosis of the cancer, the person's expected life expectancy, their average life expectancy, was maybe increased by 1 full year. And we might conclude from this that our treatments have gotten better, that our treatments have gotten more effective because people are living a year longer than they were, say, 10 years previously. But there are actually two ends that we're looking at, right? We're looking from the start of the diagnosis to the end of life. And we could have gotten a larger interval there by pushing end of life back. In other words, the same person, had they existed 10 years earlier or 10 years later, would have lived to a different age. On the other hand, we could be pushing the start earlier. Maybe we're getting better at detecting things, right? Maybe, and this also plays into detection bias. If we get better at detecting, say, cancer or something over 10 years, then from the time of diagnosis through end of life, that person's going to live longer because diagnosis just got pushed forward. And probably in reality, it's going to be a little bit of both, right? There's going to be some effect of us getting better at detecting the disease and some effect of us getting better at treating the disease. So we're probably pushing both ends out a little bit. There are many, many other examples of bias, but I think that it gives a lot of different examples. And I think this is one of the more interesting slides in chapter 1, because you can see how many different ways just the fundamental ideas of statistics that we're going to be using for the rest of the course can go wrong, right? This whole data collection or analysis can go wrong in a lot of different ways. And this is a field with a lot more gray areas than, say, something like algebra or calculus, right? We have to be cognizant and aware of a lot more things, and we have to make kind of judgment calls, right? Like, okay, if I look at this data set and I see that it was put together by somebody who has a strong incentive this direction, or who maybe doesn't have expertise in this area and might have incorporated some bias, is it so bad that I just throw the whole thing out, or do I take it with a grain of salt, or do I think that they've corrected for any of that? Okay, so that is the second to last slide. Any thoughts on that? Any questions? All right, and then the third slide, I just kind of roughly labeled statistics. One example that we're going to see in chapter 3, but this also applies to other examples in chapter 3 and in chapter 2 is, well, when I'm taking a data set, maybe it's 100 data points, maybe it's 10,000 data points, and crunching it down to say one number or one picture, if I want to report something like a measure of center in chapter 3, well, I have a lot of different options. Should I report the mean, the average? Should I report the mode, the median, the mid-range, something else? There's lots of different measures of center. Why? How should I choose it? I mean, I suppose I could report them all, but if I have a data set of size 100 and then I try to report some descriptive statistics to you and I report 10 measures of center and 5 measures of variation, and well, I mean, now I haven't done a good job of describing the data set, right? Maybe there's a good reason to choose, say, the median instead of the mean. That might be clear, but if I think that that's the right choice, do I choose the mean instead because it makes my argument look better, right? Or maybe it would be clear if I knew that the median was the better one in this case, but maybe I don't know that. So even though we have precise definitions for a lot of these things, the decision of which measure to present, to compute and then present, is still a human decision, right? Another issue is inconsistent units. We'll talk a little bit more about this in chapter 2, but two main examples here. One is, again, starting off with kind of a silly example that's maybe a little more memorable, is say degrees Fahrenheit versus degrees Celsius in temperature data. Let's say you have some weather stations around the world that are reporting the temperatures in some app, and you make a program that combs through the different areas in that app and grabs the temperatures and computes something like an average global temperature today. Well, if the app is reporting some of those temperatures in degrees Fahrenheit, maybe like for the US, in other areas, it's reporting degrees Celsius for like probably everybody else in the world. And if you just take those numbers, the number of degrees Fahrenheit or the number of degrees Celsius, and you just smash all the numbers into one table and compute an average, well, we have inconsistent units here. We have some of our numbers are in degrees Fahrenheit, some in degrees Celsius. In essence, when we average together numbers, we're kind of trying to add them together, but we can't add together different units. We really ought to convert everything to one or the other unit first, and then do our work. So that's kind of an obvious example maybe, but still one that we should think about. A less obvious example is if you ask, if you look at, say, the S&P 500, and we'll do this in chapter 2, you look at a graph of it, and you look back at the Great Depression, and you look at that time and you say, wait, like, it was just kind of a tiny blip in the S&P 500. It didn't seem like that big of a deal, especially compared to, say, the dot-com bubble, 99, 2000, or the housing market bubble, 07 to 09-ish. The Great Depression looked a lot less great. But really, what's the cause of that? Well, even so, the S&P 500 is essentially measured in dollars. And even though, we're looking at 1930 dollars versus 2025 dollars, it's still the nominal unit of dollar. In some sense, it's the same unit. But in 1930, I mean, a dollar could buy you a lot, right? I remember my dad telling me that when he was a kid, like, his mom would send him down to the store to get bread, and she would give him 2 dimes, and that was enough to buy 2 loaves of bread, and he'd have 2 pennies on the way home. And one day he got in trouble because he he wasn't given any pennies, and it's like, all right, I guess that's okay. Like, he was a kid, he's not going to argue with the person. And bread had gone up from 9 cents to 10 cents a loaf, and this was probably 1955 or 56 or something, right? And today, like, one loaf of bread costs what, a few dollars, $3, $4 or something like that. So even though nominally they're the same unit, dollars, they really mean a different thing, right? Just because of inflation. If you're looking at data over more than maybe 5 years apart, you probably ought to take into account inflation and try to kind of bring everything up to maybe up to present day value, or to some date that is sensible. So we probably ought to take these $1930 and reframe them in terms of $2025, and the same with $1999 in the dot-com bubble, and the same with 2007 dollars in the housing market bubble. Bring everything up to $2025 to present day value. And then all of a sudden we see, oh, okay, yeah, the Great Depression actually was much more significant than it might look like if we draw a graph and we have 100 or more years of values. We're really almost comparing like 100 different units on the same graph. And that's probably not the best way to go about it. And then one that you see all the time is things that are, statements that are made to sound statistical, but often don't actually say anything. So how many times have you seen something like this, taking this medication may reduce the risk of heart attack and stroke? Well, anything may do anything. You know, one thing to think about is this statement falsifiable? In other words, could I do an experiment and basically give strong evidence that this statement is wrong? Not really, right? I mean, anything may do anything. If I give a whole bunch of people this medication and their risk of heart attack and stroke doesn't seem to decrease, well, I don't know, maybe you just didn't find the folks that it works for in your study. Things like this, college grads are 30% less likely to be unemployed. So less likely than whom, right? Than non-college grads. That's kind of what we're presuming that they're comparing to, but if they don't actually say that, we don't really know what the comparison is here. This is just something that's kind of irksome, but something like wearing your seatbelt reduces the chance of dying in a car accident by 400%. Well, you can't really reduce something by 400%. If you reduced it by 100%, it's impossible to die in a car crash then. Right? If you reduced it by 25%, it's 25% less likely. Or if you reduced it by 50%, your risk is cut in half. This is more important on the other side. When you say something was increased by 300%, does that mean that one unit went to 3 units, or does that mean that one unit went to 4 units? That can be a really big difference in some contexts, right? If you say, whatever, the amount of money I have in my account is increased by 25%, it means every $100 I had is now $125. If you say it's increased by 100%, then every $100 became $200. So if you say it's increased by 300%, it really should be that every $100 is now $400. But often people mean multiplied by 3, that every $100 is now only $300. So you have to be very careful when you're using things like percent increase and decrease to use it properly and to be really clear about what exactly is being said. Things like this that we all see, like save up to 30% or more, right? You see that kind of thing all the time. It says nothing. Save up to 30%, in other words, 30% or less, or more. So you can save 30% or less, or you can save 30% or more. So it really doesn't say anything. And this just kind of irked me how this was phrased. It says, I was reading some, government thing about, I think it was applying for a job or something like that. And it said, applicants must be at least 21 years of age or older. So I don't know. It's like, be careful how you phrase things. You can have all of the really good statistical and mathematical and all of that support behind everything, you can have a really good argument ready to go, and then just, with one careless phrase, kind of throw it all out the window. And then lastly, misleading graphs, which we will talk about in chapter 2. Any questions on anything from chapter 1? Okay. Let me pause my share here and bring up chapter 2. Anymore, like all of these Microsoft Windows have so much stuff on them, it's almost impossible to find a place you can like actually click and drag to reposition a window. Every time I click something, it like does something.
I agree. They're very overcrowded.
Yeah, I like minimalist stuff to an extent in some parts of my life, and yeah. Okay, so any questions, thoughts, anything about chapter 1? Okay, moving on to chapter 2 then. Similar to chapter 1, like chapter 2 you see has 65 slides. Some of them are going to go very fast. Some of them we'll spend more time on, so it's not going to be 65 slides like the last 3 that we spent quite a bit of time on. Okay, so moving into chapter 2, we are now moving into the discussion of descriptive statistics. So chapter 2, more about the kind of graphical side of descriptive statistics, and leading into that, how we can organize data to make those graphical techniques, let's say, feasible to create. And then we're going to move into chapter 3, which is more about the numerical descriptors. So things like reporting an average in chapter 3, or reporting, say, a histogram in chapter 2. But really the focus of chapters 2 and 3 is to take a data set, which we kind of imagine as being a large bunch of data, a bunch of raw data, maybe 100 data points, maybe 1,000 data points, and crunching it down to something much more easily digestible, maybe just one picture or maybe just one number. Now, of course, for our examples, we're going to use small data sets, so we might be only using 5, 10, 20 data points, but we typically imagine that we're using a lot larger data set. So, but because we want to be able to do some of this stuff by hand and have it obvious what's happening in class, we'll use smaller data sets, and in the homeworks as well. And to start off chapter 2, or really kind of wrap up chapter 1, here's a quote from Sherlock Holmes, the detective written by Arthur Conan Doyle, I guess late 1800s, I suppose. And he says, "It's a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts." So any thoughts on this? I read this when I was reading one of the Sherlock Holmes stories, and I just thought it was a very interesting statement. Any thoughts on this quote from Sherlock Holmes or Arthur Conan Doyle? Do you think it's right? Do you think it's wrong? Should we never theorize before we have data? Well, on one hand, if we should never theorize before we have data, that kind of almost throws all of science out the window, right? Because the whole scientific method is we come up with a hypothesis, and then we derive an experiment that's capable of disproving our hypothesis, and then we do the experiment to get the data to kind of evaluate our hypothesis, or to feed back into our hypothesis. So on one hand, I mean, is Sherlock Holmes saying that science is a bunch of just a bunch of baloney or whatever? I don't think so. I mean, Arthur Conan Doyle wrote Sherlock Holmes to kind of be in like, I guess his part-time work when he wasn't being a detective. He did like experiments in chemistry and things like that. So I don't think this was intended to be a slight against science. But I think the important factor here is that Holmes primarily is a detective. So he's typically coming into a scene after the fact, after the crime has been committed. And what kind of study, in a sense, is he doing? Well, he's doing a very observational study. So he's looking around to see what are the things that stand out to him that he finds interesting. Well, if he goes in and based on what somebody told him before he sees the scene, if he already says, oh, okay, I think I know what happened, then is he likely to be led astray by confirmation bias, that he's going to have a theory in his mind and he's going to say, oh, that looks a little off, but not a big deal because it doesn't fit in with my theory. But this thing looks a little bit off, and oh, that's the thing I'm going to focus on because it does confirm my theory that I think happened, right? So being on the more observational side of things, I think this does make sense for Holmes. Keep your theories under wraps, or maybe not under wraps, that's not the right word, but hold off on making any theories, just collect the data and let the data lead you. But obviously, with the more experimental approach, an experimental study, you kind of have to have something that you want to test or a theory because you need to figure out what levers you want to pull, right? Um, I mean, at the very least, say like in a pharmaceutical trial, you need to decide what drug you think is going to work and for what reasons before you start giving it to people or animals. So I thought it was kind of interesting that, Holmes most of the time being doing what we might call observational studies. This does make a lot of sense, but in the realm where he's doing experimental studies, you kind of have to theorize before you have facts. But this does bring up that caution of confirmation bias that when we're doing science, we have to be very careful and always have the mindset of trying to disprove what we think that we know. Okay, so moving into the chapter 2 material now. So at this point, we've concluded chapter 1. From this point forward in the course, we're always just going to have in our mind that somewhere we have a raw data set. We have a bunch of raw data. We got it somehow, maybe a survey, maybe, you know, uh, just observational, whatever it may be. We somehow have a raw data set. And in chapters 2 and 3, our goal is to take this bunch of data, this may be 100 data points, maybe 1,000 data points, and crunch it down to something that's more informative. So our end goal in chapter 2 is to create some kind of graphical representation. So maybe a histogram, maybe a line chart, maybe a pie chart. But before we do that, we have to organize the data first. And that's where frequency distributions come in. So the raw data is the data in its original form. A frequency distribution organizes the raw data in a tabular form. You can kind of start to see that, well, Excel is a big table. So like this is where, Excel starts coming into play pretty nicely, helping us organize data and do things with data. And it uses these ideas of classes and frequencies, classes being, in a sense, the bins that we put the data points in, and frequencies, in a sense, being the number of data points that ended up in each bin. So here's an example. Suppose we do a food survey. We ask people, which drink do you prefer? A, B, C, D, E. This is clearly categorical data, right? It has no natural ordering or ranking. And these are the responses we get back. First person answered D, second said that A was their favorite beverage, and so on. We see we have a 5x5 grid here, 25 responses. Again, we're working with smaller data sets here, but we would often imagine this grid maybe containing 1,000 data points. And maybe I'm a buyer for a local supermarket and I want to decide, well, how much of each of these should I buy? Maybe I don't have a lot of data. Maybe this is a fairly new supermarket. So we just did a market study and how much of this should I stock on my shelves? So what I might do is simply write out my classes. The classes are the bins, um, the things that I'm interested in. So in this case, my classes are pretty readily described. Just drink A, drink B, drink C, D, and E. And then for each class, I find its frequency. In other words, A occurred 7 times. We see once in the first row, twice in the second row, twice, once, and once, making 7 A's in this set of 25 data points. So we see class A has a frequency of 7. There were 7 folks who preferred drink A as their favorite drink. B occurred 4 times, C 5, D 3, and E 6 times. One thing that's always a good idea when we construct a frequency distribution is to add our frequencies together and get a total and make sure that that total adds up to our sample size. In this case, it does. We see we have a 5 by 5 grid, 25 data points. We have our list of frequencies that adds to 25. Those two numbers mesh. So, it's not a perfect check that we did everything right, but at least gives us some confidence. So I could look at the frequency distribution here, A7, B4, etc. Or I might want to look at a relative frequency. Maybe I'm combining some different markets together, and maybe I have some different raw data sets that are of different sizes. And I would like to know, do I think that people in this area tend to prefer drink A more strongly than people in this other area? My data sets are different sizes. It can be kind of hard to compare them together. But maybe what I can do is I can say what percent of all my responses answered A, and that might be easier to compare across different regions, especially if I have different sizes of data sets. So I see that A has a frequency of 7. There were 7 individuals who answered A out of a total number of data points 25. So 7 over 25, we can multiply top and bottom by 4 to get 28 over 100, or 28%. So that's where that comes from. 7 individuals preferring A means that 28% of our sample preferred A, or 16% of folks in our sample preferred B, 20% C, 12% D, and 24% E. So we could either list frequencies themselves, 7, 4, 5, 3, 6, or we could list relative frequencies or percents, like these 28% and so on. And again, there's costs and benefits to both. Now let's consider an example like this. Let's suppose that I have an exam, say Unit 1 exam, gave the exam, graded the exam, handed the exam back, and these were the grade data, let's say. And we can probably tell by looking at this data, or maybe guess by looking at this data, that it seems like the grade data is in increments of 0.5. So we might look at this and we might say, well, I have something that's like discrete data, right? I mean, you could have got a score of 0 or 0.5 or 1 or 1.5 or 2 or 2.5. So on all the way down to 99, 99.5, 100. And I might say to myself, well, I guess I could enumerate all of the possibilities and do the same thing I did here, right? Count up the same way that I counted up how many people got A here. Just count up how many people got a 0 here, none. How many people got a 0.5 here, none. How many people got a 1, none. We can see the problem with this approach, right? So if this was my class and frequencies, I'm going to get a whole bunch of zeros and then a 1 and a whole bunch of zeros and then a 1, and maybe somewhere I'll get a 2, right? This doesn't help me at all. This doesn't help organize the data. This doesn't help crunch the data set down to a more manageable size. This actually makes it a lot worse, a lot more confusing. So I could force the issue. I could, in a sense, treat this like almost like a discrete variable. But it makes a lot more sense to treat it almost as a continuous variable, because does anybody care that much if they get, half a point more or half a point less? Probably not too much, right? The difference between a half a point is small on the scale from 0 to 100, right? This would be 201 classes, and I only have 25 data points. That's way too many classes for the number of data points I have. It makes a lot more sense to group these together. To say, okay, I have grade data that could span from 0 to 100 in half-point increments, makes a lot more sense for me to group them together in a meaningful way. I might choose to group them this way. I might choose to group them into classes that look like 89.5 to 100, the kind of A's, so to speak. The B's, maybe 79.5 to 89. The C's, and so on. I see that each of these classes is about the same width. This contains about 10 points. This one contains about 10 points, 10 percentage points or 10 grade points worth of size that I'm grouping together there. They're about the same width. I mean, you might argue a little bit about, this goes up to 100 and not whatever, 99 or something like that, but they're pretty close to the same size. So when we group classes, when we group outcomes together to make classes, we want to do it in a way that's kind of reasonable, that's kind of sensible. In this case, we have a nice correspondence between, say, letter grade and numerical grade. Maybe that's something that's meaningful to us. We want to group together so that we don't have too many classes. I think typically if you get above 10 classes, unless you have a really good reason, it just becomes too much to really parse, to really make heads or tails of. We also don't want to have too few classes. I mean, you can imagine if I made this like 0 to 50 and 50 to 100, like everybody's just going to be in the 50 to 100 class. Like that's not fine enough. That's way too coarse. It's not fine enough to see any of the detail. But something like this is way too fine. It's so fine that it's just there's so much fine detail here that I can't make heads or tails of anything. It's almost like deciding what magnification to take, right? Did you ever do those kids books where they're like I forget what the magazine was called. It was like a highlights or something like that, where occasionally they would have a like really zoomed in something, like a little picture of something really zoomed in, and you had to like try to figure out what it was. It's almost like that, right? Over here. But we also don't want to zoom out so far, if we don't want to zoom out and just be in outer space looking down at the earth. We want the appropriate number of classes. So I think typically something like 5 to 10 classes, is usually a good thing to shoot for, and usually trying to make your classes about equal size. Now, one exception to the kind of equal size rule is our kind of Fs here, 0 to 59. This is a pretty big class. It's much bigger than the rest. And then it contains something like 60 grade points, where the others contain something like 10. But I see that that's kind of sensible here because there aren't too many folks who scored below 60. There's like this 55.5, this 57 maybe, this 56. But it's almost like 0 to 50, there's no real utility in putting a whole bunch of classes there and having 0 frequencies associated with them. So sometimes at the ends, either the bottom or the top or both, we have a bit of a catch-all category, right? Or maybe there was one person who did really terribly and got like a 7%, but we don't want to have like, a whole bunch of classes with 0 frequency so that we can get down to that one class with 1, at least most of the time. Again, maybe there's a really good reason that you're doing that. Maybe you really want to point out, the couple of folks who did really poorly, and maybe you're looking at strategies to kind of help them out and maybe help them to do better on the next exam or something. So if you have a really good reason to do that, maybe that's valuable. But in this case, we'll use kind of a catch-all here at the bottom. The other thing that we want to be cognizant of, if we're being a little sloppy with our class limits, say 90 to 100, 80 to 89, or the A's, B's, C's, D's, and so on, well, we want to set up our boundaries of our classes in such a way that every potential data point falls into exactly one class. So you notice that I ended this one at 89 and started this one at 89.5, and our resolution here is 0.5. Like our measurements jump in increments of 0.5. If I left this one at 89 and made this one 90, somebody could score at 89.5 and kind of fall through the gaps and not get counted. Or if I made this go up to 90 and this started 90, then somebody who scores exactly 90 might get counted in both. We don't want to double count data points. We don't want to miss data points. So we want to make sure that we establish these boundaries correctly. If we have a really continuous situation, like say people's heights, we might use like a closed to open interval. So like a half closed interval, maybe like 60 inches to 61 inches, and then 61 inches included here, but not included there, to 62 inches. So we might use half open intervals for our boundaries. If we had something like this, where say measuring height, we could get more decimal places of accuracy with better tools. And height would be another good example where you want to include a catch-all. There might be somebody who pops up that's like 7 feet tall or that's like 4 feet tall, but I probably don't want to have 1 inch classes all the way up to 7 feet tall or all the way down to 4 feet tall just in case. I would include a catch-all. I pick, a relatively short height, maybe like 4'9" or something, and then just say anybody below that, or a relatively tall height like 6'6", and say anything above that falls into that class.
Sir, I have a
Yeah.
question.
Mhm.
Can you please, again, I mean, give me a concept of like class limits and boundaries? I'm not able to understand it completely. Like, if we have 89.4, where can you include that? I mean, in which class?
So that's a good point, is if we had 89.4, what do we do? So an assumption we made here, either by looking at the data and making an inference, or even better by kind of knowing how the data was created, is that these are incremented in 0.5. So you can only get like 89 or 89.5. It's literally impossible here to get 89.4. So it's like this would be, maybe when I decide to grade an exam, I say I'm only grading, on the half point increment. So if I have a paper exam that I'm grading, like if I'm going to take off points, I'll take them off in half point increments, but I'm never going to take off like a 0.1 point increment or something like that. So that could be a decision we made. But if that wasn't clear, if we weren't sure, how the individual was grading this, or we thought that it was possible to get something 0.4 or something 0.1, or maybe even something 0.15, like sometimes my stat lab will divide up the different parts for a problem kind of in a funny way. So if I make a problem, that has 3 parts, so I make it 3 points, it'll give 1 point to each part. But if I make it 4 points split over 3 parts, it'll be like 1.33, 1.33, and 1.34. So if we're not sure how it's split up, we might do something like this, using half open intervals just to cover our bases. So this would say every number that is from 60 up to 61, but not including 61. So 60.9995 goes in this interval, but 61.000 jumps over to this one. So if we were kind of certain about the discrete nature of the situation, that I'm jumping in units of 0.5, I can safely do something like this, because I know that it's impossible to be strictly between 89 and 89.5. Like 89.2 is not possible if I know enough about the context. But if I didn't know that context, I would have set it up something like what would I do? Maybe 90 to 100. I should use a comma there. And then 80 to 90, open parentheses. So this is an open interval on that side, and this is closed. So if somebody scored exactly 90, they would go here. But if they scored any less than 90, even a little bit, they would go down here. And then I could do, 70 to 80 where that's open. So I could do something like that. Yeah. So I would only want to do this if it was very clear to me, either from the context or from my surrounding knowledge of the scenario, that I had increments of 0.5. Yep. Okay. And then I count the frequencies the same way I did earlier. I just think of these as like bins. Any data point with a value of 89.5 up to 100, including those endpoints, gets counted in this first bin. And there were, say, 9 of those values in this first bin. So this, the 100 gets counted there, the 97 gets counted there, the 91 gets counted there. And if we went through all of these, there were 9 of those data points that had values from 89.5 to 100 inclusive. And there were 5 that had 5 data points that had values 79.5 to 89 inclusive, and so on. A cumulative frequency distribution is kind of similar in nature to the previous frequency distributions, where we have a certain class that we're discussing and then a frequency related to that. But here kind of, oops, scroll down on the wrong thing. Here kind of, instead of thinking of, I have like a line where my data live, and up above, I was kind of splitting it into bins. Imagine my bins are about the same size and don't have spaces between them, but right, this was kind of the structure up here. In a cumulative frequency distribution, what I have is I have an ever expanding bin. So I have one bin that includes some swath of my of where my data could live. The next one includes all the stuff in the previous one plus some more. The next one includes everything plus a little bit more. And then a little bit more. And then eventually we should get to where our bin is wide enough that it covers all of the data. So I could construct my cumulative frequency distribution this way, or I could do it the other way. I should have done it the other way to make it consistent with what I had over here. I could construct it this way as well. So the people who got, say an F or below, the people who got a D or below, a C or below, B or below, or an A or below, which of course should be everybody. So my class less than 60, maybe I'll say that this range is from 0 to 59. So anybody who scored from 0 up to and including 59 gets counted in this bin. And there were 5 of those folks. The less than 70 class includes all the previous people, the 0 to 59s, plus potentially some other folks who scored 59.5 or 60 all the way up through 69. And it does turn out, oops, there we go. It does turn out that we had none of those folks. Nobody scored between 59.5 and 69. So we don't accumulate any more folks by expanding this bin. There were 0 folks in here. So when I expand my bin out, I don't pick up anybody else. But the next time I expand, when I look at my less than 80 bin, going from 0 to 79, so 69.5, 79, or sorry, 78.5, 79, etc. 69.5 all the way up through 78.5, 79. They all get counted now, but 79.5 or 80, they don't get counted here. Well, we saw that there were 6 folks who scored from 69.5 to 79 inclusive. So there were 6 folks in this bin. They've now kind of been picked up, right? There were 5 folks here. This was 5. 5 plus 0 is 5. But 5 plus 6 more is what gives me 11. So this cumulative frequency distribution, instead of jumping from one bin to the next bin for our frequencies, we're taking a bin and then increasing its size incrementally. And of course, by the time that we cover the entire data set, our biggest bin should include all of the data points, which was 25. And again, that's a good check, right? Just like in our normal frequency distribution, we add up the frequencies and check that we get a total that's the total number of data points we have. For our cumulative frequency distribution, for our kind of everything included bin, our last bin that goes from 0 to 100 in this case, we should have a cumulative frequency of 25. We should have accounted for all of the data points, and we have. Any questions so far? So we looked at frequency distributions for categorical data, where there's really no natural ordering or ranking. We can just list, A, B, C, D, E, or the, names of the drinks or whatever it may be, and count the number who chose each of those. We have grade data where we have a natural ordering or ranking. That ordering means we can group things together, right? Note that it wouldn't make sense to group together a categorical frequency distribution. There's no natural ordering or ranking, which means there's no natural sense of which ones are close to one another and which ones are far away. Now, maybe we can, impose some kind of ordering or some kind of closeness if we know more about the context. Maybe if we had like Pepsi and Coke, or like Sprite and 7-Up, maybe we say, oh, Pepsi and Coke are kind of the same, or Sprite and 7-Up are kind of the same. But that's really using a lot of context information. If we just look at the data, there's no natural ordering or ranking or sense of closeness. So we really can't group anything in categorical, right? When we have a natural ordering or ranking, we do have a sense of closeness. So once I rank things that are ranked kind of closer together are kind of closer in a sense, we can start grouping things potentially. Now we might look at something that's kind of numerical, something that has a nice ordering to it. Something like a star ranking, provide a satisfaction rating from 1 to 5 stars. We might say, oh, this can be ranked. It has a natural ordering to it. 5 stars is more satisfied than 1 star, for instance. I could group it if I wanted to, right? I could make a group frequency distribution like this. I could group maybe 1 and 2 together, and 3 and 4 together, and then 5 is kind of off by itself. But actually in this situation, even though I maybe could group it, it has enough structure to possibly group it. It doesn't actually help me at all to group it. I'd actually rather just almost treat this like categorical data. How many folks answered 1 star? How many folks answered 2 stars, 3, 4, and 5 stars? Right, these were the responses down here. I'd rather just list all of the possible responses and their frequencies, and perhaps their percents as well if I wanted to. 1 person gave us a 1-star review, 3 gave us a 2-star review, 2 gave us a 3-star review, and so on. This probably makes more sense for this data set because there's just such a small number of possible responses. This really feels like discrete quantitative data, where the jump from one response to the next, from 1 star to 2 stars or 2 to 3, is like a pretty substantial jump, right? We might argue that this is discrete quantitative, but again, the jump from 59.5 to 60, or 60 to 60.5, not a very big jump. There's a lot of gradation there. We treat it almost more like a continuous variable where we group things together versus this where we just enumerate all the possibilities. Now, one thing to note is if we had actual categorical data like our drinks, our beverage preferences, there's really no good or bad way to list them. Whether you list Pepsi first or Dr. Pepper first doesn't really matter. If I do have a natural ordering, I probably want to respect that ordering, right? I probably want to either list my classes as 1, 2, 3, 4, 5, or maybe 5, 4, 3, 2, 1. But I probably don't want like 4, 3, 2, 1, 5. That would be kind of a silly way to rank, to list the classes because they do have this natural ranking to them. So I probably want to respect that ordering when I list my classes, either 1, 2, 3, 4, 5 as my responses, or maybe the other way around, but not jumbled up. If I jumble up Pepsi, Coke, Diet Coke, root beer, whatever, it doesn't really matter because there's not a real underlying structure there. But there is an underlying structure here. We should respect that in both the frequency distribution and in the graph that comes out of that. If we make a histogram or something, we probably should respect that there as well. So we're kind of a little bit treating this like a categorical distribution and but also respecting the fact that there is a little more structure here. We should respect that when we make the class listing. Any questions so far? Okay. All right. I think maybe we will end a few minutes early today because I don't want to kind of jump into the next big topic, building off of these frequency distributions, actually creating the graphical representations. With only about 12 minutes left, I feel like we just get started into it and then have to restart it next time anyway. So we will leave graphical representations of data for next class. And unless there are any questions, we will end a few minutes early. Let me stop the recording. I do see there are a couple